All right, welcome to Algorithms Live. And this week we have should be an exciting episode for a lot of you. This has been a requested topic over the past few weeks. Is this divide and conquer on trees technique? It's also known as centroid decomposition, and it's basically a way of attacking a certain class of tree problems, and you can extend it to work on other types of structures as well. So. I also added an extra problem to the blog. So if you're interested in this technique and you want to see a little bit more of what's going on and you want to try some extra problems, there's 3 in the blog now. We're just going to go over the first problem. It's going to probably take us the whole episode to dive in and tackle this. But I'm going to start off with an easier variant of that problem and then dive in a little deeper. Next week is really exciting because the last few weeks we've covered, we'll have covered this technique, divide and conquer on trees. We've also covered this convex hole optimization technique. Next week, Lewin Gan is going to be back on, and we're going to talk about his problem, yet another tree problem. And it basically combines these 2 techniques into one problem, which is really neat. And that's what we're going to talk about. We also have different approaches to this problem too, completely different approaches. I don't fully understand his solution. He doesn't fully understand mine. So it should be a really interesting discussion. And next week, what we'll talk about is centroid decomposition trees a little bit. The actual data structure you can form from this divide and conquer pattern. So it should be a good thing to pair together. So if you're interested in the data structure you can form from this technique, definitely tune in next week. But you definitely want to know this technique before learning centroid decomposition trees. The last thing I wanted to cover up on from the previous week is there was a bug in my solution at the end of the last episode. If you saw, I was struggling with it. It's a 1-character bug. So if you were coding up my solution or playing around with it, I put it in the blog, just the 1-character fix that you need to make. I had a greater than sign that should have been less than, or vice versa. So hopefully we won't have any bugs today. I'm actually going to code this problem, this yin-yang paths problem from USACO today. And hopefully we won't have any bugs. I think this one should be a little bit easier to live code. All right, so let's just dive right in terms of what this is going to cover. If you saw episode 1, I talked about a ton of properties on trees, and that's what we're going to go back to here, is this special type of node in a tree called a centroid. And we want to know what defines a centroid. Well, that's just a node whose removal guarantees that the largest subtree is as small as possible. And so that's out of all the nodes you can remove. So if you're looking at a tree like this, for example, if I try removing this node up here, you get a pretty big tree. You get 1, 3, 5 nodes. But if I remove this node right here, the largest subtree only has 3. And so what we're looking for is nodes like this, or nodes like this. And you'll notice this graph has 2 centroids. You can prove that the graph has at most 2 centroids in any graph, and they're going to be right next to each other. So it's very similar to the property of trees. And if you want a more in-depth coverage of centroid, you can go back to episode 1, the trees episode, and I give a little bit deeper coverage there. And particularly how to find the centroid. So I'm going to focus less on how to find the centroid, although I'm going to code finding the centroid today. So if you want to know how that works, you can go back to episode 1 and view the pieces on centroids. But the big property on centroids that really drives this divide and conquer approach is the size of the remaining subtree is at most 1/2. So we cut the tree in at most half. This is really popular in terms of computer science, cutting things in half, or at least half. Binary search, it runs off of this basically. And then particularly merge sort. So if you remember when we were talking about segment trees, I drew this picture of merge sort's runtime. It does a linear amount of work on each level, but then it splits the array in half. There's a linear amount of work on that level, splits the array in half. There's a linear amount of work on that level, and continues. And you'll notice that this side right here is log n in depth, was part of my argument, and the width here was n. So our runtime was actually n log n for merge sort. Well, when you're doing divide and conquer on trees, you're not necessarily splitting it in half. You're going to be splitting it into a bunch of different pieces. So if I was going to draw the same picture, I might, or a similar picture at least, I might have this linear amount of work, cut the subtree in half, but there might be other pieces of the subtree that are a little bit smaller. And so maybe this piece gets cut in half, and this piece gets cut in half. And so they're not necessarily contiguous in the tree in this like nice strip form. I'm just like grouping them by how they get cut. And you'll notice that this is actually a little, like we're actually saving some runtime here by things getting chopped up to be smaller. So the actual worst case runtime is when you group the branches that are, like you're separating these branches out here. If you group them all into one branch, so it's like you have your biggest child that's at most half, and then you have everything that remains, you can do a sort of upper bound analysis on it, even though it's being chopped up in all these really weird positions. So what I like to say is I like to think that imagine these branches over here are all being merged together. And then you basically start analyzing it merge sort style in terms of the runtime. So if you write out a recurrence for the runtime here, so T of n is 2 times T of n divided by 2 plus some amount of work on the level. So it might be order n work in the case of this, or it might be something else. Our complicated divide and conquer on trees code could be some summation. So these are my component sizes. So if I take all my components and sum them together, what I'm left with is some problem that is size s, which is my component size, plus some amount of work. And the key observation here is T of n is always going to be greater than or equal to m of n. So if you're dividing things to at least half, you can just do the analysis like you were dividing it in half, and it'll come out to give you a good runtime analysis, or at least an upper bound on the runtime analysis. So your fancy master theorem or whatever you want to do. So if you look up Master's theorem, it has to meet a certain form. This is definitely not the form for Master's theorem, but this one is. So what I can do is I could do something like, if I'm cutting it in half, like so, 2 subproblems of n divided by 2 in size, and I do O of n work, then this can come out to n log n. And then even if I, let's say in the subproblem, if I do n log n amount of work inside, if I solve each subproblem on the tree that remains, and n log n time, then what I get for my running time is n log squared n. And again, you can just use Master's theorem to work that out, or if you know iterative substitution, you can kind of figure out where that runtime is. It's best to have a few of these memorized. It's easier just to like think in context in terms of what you're going to do. So that's basically what we want to do, is we want to have in terms of this divide and conquer, we have a tree we'd like to analyze. And what we'd like to do is remove some node from the tree and solve the subproblem on this tree right here, remove some node, and then solve it on the subproblems that remain. So I'll solve the subproblem with this node, remove this node, and then solve it on each of these remaining subtrees. And there's a very specific pattern that this tree divide and conquer ends up having. So I'll write out the pattern a little more specifically. The first thing is we're going to solve the problem for all paths going through some node. The second step is then when we remove that node, because we've already hit all the paths that went through this node that we tried. So if we were counting the number of paths, for example, that went through this node in some form, then what we could do is just count the ones that pair things together and get that done. And then we remove that node, and no path can go through that node anyway that we haven't already counted. And now we can solve it on the subproblems. And then the step 3 is solve those subproblems recursively. And that's really the pattern that we have here. So let's dive into a problem, because this has gotten really theoretical really fast, and I really want something a little more concrete. So there's this problem here on USACO called yin-yang paths. And hopefully you read it from the blog, but maybe not. I'll describe it here in simpler form. So I'm not going to give you the full problem yet. I'm going to give you a much, much easier version. So here's the idea. Here's my easier version of this problem. You have a graph. You have some black edges and some white edges. And they're described as cows being on paths. And what I want to do is I'd like to, given a tree, some of the edges are weighted black, some of the edges are weighted white. I want to count the number of balanced paths. And so a balanced path is the number of yin equals the number of yang in terms of number of edges that are used inside that path. So num yin equals num yang, you're good. That's a path you should count. So I could look at this graph. I want to see how many paths are actually on it. So you should probably count that here. Well, there's at least this one. I could also pair these 4 different ways, right? Something like that. There's 4 different ways to go there. And then I also have those 2 paths and these 2 paths. So there's paths that end in the leaf nodes. There's paths that end in the root if I'm rooting this tree. And then there's some paths that are going around. So in this example, there are 9 total paths. Okay, so as it turns out for this problem, all the paths go through the centroid right here. But that's not always going to be the case. And we want some strategy for figuring out how to count the number of paths that actually matter. So I'm going to draw a more complicated tree. And we're going to see how we can attack this problem of counting the number of paths that go through some node we're guaranteeing. So we're going to make that node the root node. So we're going to use the technique of rooting the tree. And I just want to count the number of paths that go through that rooting of the tree. And my root I'm going to pick as the centroid, because that's the one I want to remove and then solve it with divide and conquer. So here's my tree. So white, white, black, black. So pretty good. And so I want to count the number of paths that go through this node. I don't want to do this in a very expensive way, if I can avoid it. I don't want to pair all paths up. I really need to keep my runtime down to linear or close to linear for this to work. And so I'll just show you a reason why. The number of paths can be up to n squared, or order n squareds. So I could have some paths, and maybe these are all the white paths on the left-hand side. And these are all the black ones on the right-hand side. And what I could do is I could just end up having half the nodes be white edges, half the nodes be black edges, and my number of balanced paths could be n divided by 2 squared. So the main thing here is it just tells us that we need to use longs, but we also need to do this counting fast. So here's what I'm going to do. I'm going to make my white edges worth -1 in weight and my black edges worth 1 in weight. And then I'm going to look at the path going down and basically say, what's the sum to get out to and including that node? So if I'm walking my path like here, I can use a DFS to find this. So if I walk my DFS out to here, this is -1. I continue walking out. I get out to -2. This comes back to be 1. I come back up my path, maybe walk over here. I also get 1 because it's a black path. I could walk this way and come out to -2, -3. Come back the other way, I could get -1, something like that. So I could end up having all these pieces that are coming out to different balancing factors. Well, and I could end up having the same thing for the right-hand side. So let's take a look at this right-hand side here. I could have 1, 2, 2, back down to 1. These come out to 1. This one comes out to 1 as well, and this one comes out to 3. Right? And so if I want to pair these things together, what I'm going to need to do is I need to do some pairings on from the left-hand side to the right-hand side. So let's take a look at this. I could look at the subtree in this form. So what I need to know is the number of paths on left with imbalance k. And I need to pair those with the number of paths on the right with imbalance k, minus k. Because that will balance the path. So I'm just going to pair this left-hand side with this right-hand side. I also have to be a little bit careful because I could have a path coming down here. Let's see. Oh, I didn't draw any. Let's draw one extra edge. So, yikes, something is wrong. Oh, this should be -1. Yikes. -1 over here, but then this comes out to 0. So this is actually a balanced path, and it doesn't pair with anything on the right-hand side. So I also need to count paths that end at the root node. That's something to also keep in mind. So you also have to add back in the paths that end in the root node. So and they'll have imbalance of 0. So we can do this pretty easily. All we do is we just make a big old array, right? And I just fill it on the left-hand side. And I'll just keep track of the number of paths that have that particular imbalance at each of the cells of my array. And then I can just query the opposite component, which is the -k component. And I can get this to pair up nicely. So I just fill the table, and then I just look at all the paths on the right, and I try to pair them with the paths on the left and work from that. And so what this will do is it'll basically just count the number of paths that go through the root node or are guaranteed to go through the root node. If they don't go through the root node, then I'll count them when I remove this node, and then I end up having the remaining subpaths. So it's important to realize that this path is not being counted right now, but on a subsequent call to the divide and conquer, it'll actually care about that path. All right, so we do have one small problem with this. We have more than 2 subtrees potentially. So right now we've got a solution. If we had 2 different subtrees, we're basically just pairing them together. So there is a way around that. What we do is we keep track of our subtrees. Like so. And so if I have different children in a rooted tree, I just say that, hey, these are all my subtrees that I care about right now. And I just keep track of what's behind me, like in some kind of data structure. So you could do this solution bag style. It could be a DP, it could be anything that you're keeping track behind you. And then you just update for paths ending in this subtree. And then once you're done with updating subtree I, you update your data structure to include that subtree, and you move on to the next one. So it's really like a DP on a sequence that we're basically getting away with here. And we just have to, in order end time for the entire thing, pre-compute this for every single subtree. So linear time on each subtree will be linear overall. And then I can pair things together. So I could, for example, so what's neat about this is I don't actually have to know what the tree looks like. I just need a sequence telling me what the paths look like. So let's say I have a tree, and these are my imbalance factors for my paths: 1, -1, and -2. Let's say I have another one that is 2, 1, and 3. Those are my imbalance factors. And then I end up having another one that's -3, 0, and -1. These are my imbalance factors. What I could do is walk through this tree one by building up my table. So I'll have my table here: 1, -1, -2, 3, 1, 2, 3. Originally, everything is 0. So I'm not going to get any paths ending at this subtree. But when I update it, this becomes 1 due to that. And I can just keep going through. This becomes 1. This becomes negative. This becomes 1 as well. When I do my queries on the very next subtree, what I can do is I can say, how many paths end in a -2? Because 2 is getting paired with -2. And so I'll end up with one path of that type. Then I come out to 1. How many paths end in -1? Well, 1 ends in that type, so I can tally that up. So then I come out to 3. How many paths end in -3? 0. So I don't add anything. So I have 2 paths so far that work. So now I need to update my table. So my table comes out 1, 2, and then I come out to 3, and that becomes 1. So now I can run through this list on this subtree and say, okay, how many things pair with -3? Well, that's going to be 3. So I get one thing that pairs with it. How many things pair with 0? Well, nothing pairs with 0. But I also have to add something with 0 because it's ending in a balanced path at my root node. So it ends up coming out to 4. And then -1 ends up pairing with 1, which there are 2 ways to do that. So I can add 2 to this answer, I get 6. So that's the way we're going to be attacking this problem. How do we handle multiple subtrees? I'm just going to pre-compute all these values for each of the subtrees. And then when I'm done with it, I'm just going to update this table that I'm going to use to store my partial solutions. Okay, so that's not yin-yang paths. So let's talk about yin-yang paths. So pretty hard problem. So the paths aren't just balanced. They're balanced paths in this problem, but we add an extra criteria. So let's say I have white, black, white, black, black, white. This is a proper yin-yang path because you can put a rest stop in the middle. So I'm looking at my balanced path. I've got white to black going forward. And then you'll notice that this sums to 0 if this was -1 and this was 1. So I add them together, it sums to 0. If I add these on the right together, they also sum to 0. I have 2 black, 2 white. It's balanced. So I have somewhere that's not on the endpoints that could be a rest stop somewhere in between. And then this is a path I care about counting. So balanced paths we no longer care about counting. Let's take a look at a few of those. We could have black, black, black. And we could have all whites. So the thing to realize here is the rest stop's not necessarily the centroid. That's something to keep in mind. So maybe the tree is rooted in a weird way. So a lot of people, when they try solving this problem for the first time, maybe this is the rooted tree. And we'll add another extra path. Something like that. You'll notice that the balancing piece of this path comes out to right here, I believe. Yes. So that's my rest stop. But if the tree was rooted right here, maybe there's a bunch of other paths that make this the centroid. It doesn't necessarily go through the centroid. So I have to deal with the fact that that path is somewhere in the middle. So that's something to worry about. Another thing to worry about, there could be all kinds of paths that have this imbalance. And so this is also one I don't want to count. There's nowhere I can put a rest stop that has an even balance, black and white cows on one side, black and white cows on the other. So how do we attack this thing? So before, what we were doing is we were taking every path behind us. So we had all paths that were behind us in the sequence of subtrees that we were considering. And we were pairing them together based on trying to get them to balance with each other. Well, now we also want to keep some extra information around. So right here, what we have is a rest stop. And over here, maybe this path has no rest stop. So we could have a partial path. Maybe it balances out to 0 on this part of the path, but then it comes out to 3 on this part of the path. And it pairs nicely with a -3 that doesn't have that balancing rest stop. So the way we can deal with this is just use 2 tables. So one table is going to keep track of the paths that have rest stops. One is going to keep track of the things that do not have rest stops. So when I do my search through a subtree, when I'm trying to get that list of information, I'm not just going to store the imbalance of the paths. I'm also going to store whether or not it balanced itself. So now we have to figure out how it balanced itself. So I could look at a path like this. So I can have a black, white, black, black, white. And we need to figure out when it balances itself. So notice there's a couple places we could put a rest stop. We could put it here or put it here. So we have to know that the path ending right here coming from the root, if this is the root, this is actually a balanced path. in terms of a rest stop. So we need a quick way we can find that. When we're doing our DFS, we always have to know, could we place a rest stop somewhere down our path or not? Then we also have cases where could be no rest stops. So in the case of all B's, right? I could have the case of all B's, or even the case of all B's with two whites. Oh, that ends up working out. There's a bunch of weird cases here, but this is one case with no rest stop. So we need some way of detecting that. So the way I'm going to do that is I'm going to keep a running sum down through my DFS. So initially that running sum is 0, then it comes out to 1, then it comes out to 0, then it comes out to 1, then it comes out to 2, then it comes out to 1. In this case, it comes out from 0, and then it ends up with 1, 2, and 3. So what makes it a balanced path? Well, if this number that we ended in was present somewhere along the path before us, then we have a path that has a rest stop somewhere. Why is that? Take a subtree up to and including that point. I'm taking the prefix up to this point and subtracting out this piece right here. It's just the prefix sum technique. If you remember that from episode 0, I just subtract out this piece. What I'm left with is the piece that ends up balancing. So if I see this number again, the difference between the ending point and where that rest stop is going to be will be 0, which is exactly what we want to detect. So that's how we'll know the potential locations for the rest stops. We could also even count the number of rest stops. If this problem was it needs to have exactly k rest stops, it might be more interesting. So something to think about. So how do we modify our DFS to handle this? So there are two approaches that I've seen. One is in the judge solution. So if the range, keep in mind that the range selected is contiguous, or contiguous on integers. So let's take in mind it's +1 to -1 on all possible edges. So we can just keep track of a range of values. And if I ever come across something that's in that range again, then I know I've already hit it earlier on my path. And so I know that my ending location is a balanced subpath. I could also keep a table of what was hit. And that's the approach I'm going to take when I go code this thing. I want to keep track of stuff that could actually be hit. All right, so now what I'm going to do is I'm just going to dive in and code this one. And that's basically how you solve this problem. So if you want to see some of the coding techniques, this is that part of the episode now. All right. So let's take a look at union paths. Yeah, let's start by reading in our graph. We've got quite a bit of code to write. So I'm going to store my graph. I'm going to make some edge class. And I have where that edge goes and its weight. I'll make a thing of edges, and that'll probably look pretty good. And I'll have some number of nodes. I'll call that n. So we will be in Java here. So I'll read in. I have to initialize my graph is a small thing here. Okay, so now I want to read in all edges. So if you remember, there are always n-1 edges in a tree. So I'll do that here. And what I'm going to do is for the black and white edges, I'm just going to take them in, multiply by 2, and subtract 1. So what this will do is just turn them into from 0 and 1, or the black and white edges, and making them 1 and -1. And so that's my graph. Okay, so I read in my graph. So what I'm going to code first is actually the pattern for finding the divide and conquer tree. Because there's basically some code that's very common every time you want to do this divide and conquer pattern. And I recommend writing your own, just like write something nice in the language of your choice that you really like. And then just abstract out one little function that you need to change to solve the problem going through a single node. Most of these problems, the pattern is just solve the problem going through the root node. So just write a function that ends up solving that. So my function is going to be called Subtree. I'm also going to pass in something called component size. But for now, I'm just going to say don't count any paths. No paths exist. But I'll keep around what the root node is. That's going to be my centroid, and what that component is. And all Subtree is going to do for me is tell me the number of paths that go through this root. And so now I can write a function I'm going to call go, and this is my recursive divide and conquer solution. So what I'll do is I typically write this in a way where I have a vertex that's an entry point. So what an entry point is when you remove the centroid, you have to identify each component. When I used to code divide and conquer like this, I used to actually make a new graph. I had a graph class. I'd relabel all the nodes. It got very, very messy. What I do instead now is I just keep an array that keeps track of, is this node been blocked off or not? Did I remove this node or not? And it actually runs a lot faster in practice. The problem testers that's in the blog, I competed in that years ago in Code Chef, and I spent a whole week trying to optimize my recreating of graphs. And I couldn't get it to pass and run in time. And now I know that this is just much faster in practice. OK, so the first thing we need to do is calculate where the centroid is. There are a number of ways to do that. You could do 2 DFSs. I like to do 1 DFS and then loop through everything that exists. So the first thing I'm going to do is do a calc sum to calculate the centroid. So the technique for finding a centroid is I need to calculate all the subtree sums that exist and basically just figure out which subtree is the largest out of all of them. So I'm going to keep around a parent for, you'll see how I code this in a second. I'm going to save my parent in my DFS coming from node I. End up going subtree sum of 1. I'm going to loop through all my edges, all that good stuff. And so if my edge is not P, then I'll calculate the subtree sum. Subtree. And I know my subtree grew based on its subtree size. All right, this is a good time, I think, to introduce the blocked array. So I like writing a sort of blocked array to keep track of what my nodes are. So I need to modify anytime I do a DFS to make sure I haven't already blocked that node. And so this is things that are in blocks used to be centroids, and they've been removed from the graph. So all I do is I loop over the edge still, but if I come across the edge that's already been used, then I just ignore it. OK, cool. So now we've calculated the subtree size of the graph that we're forming. What else do I want to do? OK, yeah, we'll go back to the divide and conquer. So what I'm going to do is I'm going to do a rooted DFS from my entry point. And the very first time I run this, I can pick any node. I make itself its own parent. That's just for convenience. It doesn't really do anything. And now I need to find the centroid. So here's what I do. So I'll say that no centroid exists. Ooh, you know what? That's probably cooler. OK. I also want to know my component size, so I'm going to start calculating that here. So what I'll do is I'll run a BFS from the entry point and figure out where my centroid is. I'm just looping over all the nodes that exist. And I don't have to use a visited array because this is a directed tree. So I'll know the size of my subtree is going to be the size of everything else minus the subtree. That's my parent edge. So basically, I want to know if I remove this node, my parent, how big is it? And then I also want to know for all my children, how big they are if I remove this node. And that'll tell me the size if things get removed. OK. So what I'm doing is I'm just looping through all the nodes in the subtree from this entry point. And I could have made this a for loop, but I only want to go over what's in my component because I don't want to do too much work. And I'm basically just finding where the centroid is. So the centroid is the one that just minimizes the size of the component that remains. OK, and so here's the rest of the recursive pattern. So I call solve tree on the centroid and however big the component size is. And that's the number of ways I could go through the centroid. So I'm solving the tree rooted at the centroid. And then what I do is I block the centroid. And then I loop over everything else that was adjacent to the centroid. And if it wasn't blocked, then I solve it recursively on that subtree. So it's almost like I'm removing this node now, and then everything that remains ends up having this subtree found. Ooh. And so that's the recursive divide and conquer pattern. And that's all really we have to do. Anytime you do divide and conquer on trees, it's going to have this exact recursive pattern for the most part. And what really changes problem to problem is what goes into the solve tree. So this right here makes pretty good hackpack code if you have a hackpack or team reference doc, as some people call it, for ACM, then this makes good code for that. So just find a way you like to implement this that ends up working, and then do that. I'm going to keep a queue around at all times. That's basically going to help me do that DFS piece. Let's see, what else do I want to do? Yeah, I need an array for subtree sizes. Yeah. All right. So I'll store some extra information. I need my parent. I need my subtree sum. I need blocked. And that'll do. Nothing else is really needed right now, but that gives me my recursion. So I'll just call go on 0, and then it'll give me the answer. So kind of appears like it could be working. What I'm going to do now is I'm actually just going to print out. This is a good checkpoint if you're typing this code up to print out what the centroids are as you're doing the divide and conquer. So what were the centroids that you found as you were doing the divide and conquer? Don't try to code this thing all in one go. You're going to have lots of bugs, and I'm trying to prevent those bugs here. And I'll do +1 because I'm basically 0 indexing them to make my life easy, but I want to read it as +1. Lots of errors. Not find symbol parent. I guess I didn't keep my parent around. Here, sure. Subtree sum really is a subtree size, though, so maybe it's poorly named. Oh well. And blocked is not an int array. It's a Boolean. Okay, so what I'm going to do is I have this this graph here called yin yang. So I'm going to just be drawing this out on paper for myself, and I'm just going to see what this graph looks like. So you should probably be drawing this out yourself too. And I just want to make sure that the centroids I'm finding are actually the centroids as it's doing the divide and conquer. So I'll write that out real quick too. That way I have less bugs. Or at least less bugs this week. Okay, so I see what this graph looks like. Let's see if it actually finds some centroids. And so the first node it finds is a centroid. I'll write these down real quick. It finds centroid 2, then 3, then 1, then 6, then 4, then 5, then 7. So let's take a quick look at what this code looks like and see if it's actually working for finding the centroids. So you can see the divide and conquer happening pen and paper style. Okay, so we have our tree. So it's a 1 here, 3 here, 1, a 1 and then a 6, 0 and then 2, 4, 5 and then 7. And this is the tree I had. And so the first centroid it finds is this right here. So it's going to solve the subtree rooting it at that node, and then it's going to just remove it from the graph. And then it's going to do a DFS on the entry points. So I don't know which entry point it's going to do first. So this would be the entry point. This would be an entry point. This would be an entry point. So here's the left recursion. So it does a for loop of recursion on each of those entry points. So the next subtree, next centroid it finds is 3. So that looks correct to me. So then it removes it from that graph. And then it does its own recursion. So it's left with 1 and 6. So then it actually finds 1, actually finds 6. Those were the numbers, as expected. Comes back up on the recursion, tries node 4, finds that's the centroid, that's good. Finds node 5, finds that that's the centroid, that's good. And then node 7 is the last centroid found. And then the graph is just deleted. So it appears to be working on that case. Probably a good idea to test it on more than just that case. I'll do something. Well, we won't worry about that actually. I won't test it further. I'll just trust that it's working, and we'll see how good of an idea that was a little bit later on. Okay. Now the hard part. So here's what I like to do. When I code my tree divide and conquer, if you're trying to debug, this is some defensive coding right here. What I do is I actually write the solution to solve tree, and I just call it on what its parameters will be. So solve tree is going to be the root. So I can specify exactly what the root is. Maybe the root is 0, make it size n, and figure out if solve tree is working separately from the divide and conquer. This way I can debug my solve tree by itself without touching the divide and conquer, plug it back into the divide and conquer and see if I get correct. So this is typically just how I code these things and debug them and get them working in contest time for this kind of problem. All right, so let's talk about solve tree. So for this problem, if you remember, there were 2 things we had to keep around to get this to work. We have to keep around if a path has a rest stop on it, or a path does not have a rest stop on it. And I want to keep track of the subtrees behind me. So I'm going to keep 2 arrays. So I'll put them in here, actually. Ooh, yeah. So what I'm going to do is I'm going to keep them on the outside. So that way I don't have to keep remaking them. And the reason I want to do that is I just don't want to waste as much memory. Our remaking memory could be slow. So this could be expensive for me. All right, so let's get some of this code working. So I have a result that I'm trying to find. This result is all paths going through this root node. I need a long there because it could be a star graph, and I could end up having a lot of things here. So if I go through all my edges adjacent to where I rooted the tree, which is going to be the centroid, once again, you have to get out of here if it's blocked. I'm going to use continue. All right, so what I need to do is I need to find all paths coming from this edge. And then I'm going to use those paths to update my answer with the tables path sat and path unsat. So I'll write this extra function here. It's called find paths, typically how I write this. And so I'm just going to make a linked list that has all the path informations for the entire subtree. If I keep a deck, you could do, I'm only using a deck. I could use array list or something else. I'm only using it because I happen to know it's pretty fast in practice. So what I'd like to do, and I'm going to make this path variable. I'd like to just do a DFS down. I want to know the imbalance of every single path starting from this subtree going down, and whether or not it's balanced itself. So let's make a path variable that'll work in our favor. And that's our path. Okay, good. So now I can find all paths ending in this subtree, because I basically have a sequence of subtrees, and I'm just aggregating that information with one DFS each time. So I just add a new path. And I'm just going to keep track if I've seen something with this exact depth before. So depth seen is going to be sum greater than 0, and that'll tell me whether I've seen it before. So let's look back at some of our code resources here. So I had this table right here like this. You notice it could go negative to -3, -2, -1, and it could go all the way up to 3. So what I'll do is I'll actually store it at position 3, where 0 is. So I'm going to modify where 0 is to make it easier to have this table, because I can't handle negative indices in Java. If you were in Pascal, you could do it, but but we can't do that here. So we're just going to keep an extra offset variable that's going to handle that for us. All right, so I have a path list, I have an offset, and this variable called depth seen is down this depth of the subtree. Have I seen this before? We look back at this case, is basically just these values. Doing my DFS down, I'm going to make it 0, 1, 0, 1. I've seen 1. I have to make it a counter, because when I'm recursing back up, I want to not erase that this 1 is already behind me in terms of my DFS. So I'm not going down just one path. I'm going down all the paths, going up and down and up and down. Every time I go down something, I'll say, oh, this is prefix sum from the root that I've seen. And every time I go back up a path, it wipes it away. So that's basically how I'm handling that piece. So I'll do a depth seen of sum plus offset. And then I'll do it the other way. Sum plus offset. I'll take it away. And you'll notice I do this after adding it to the path list. And the reason is, if I did it before, it would always be true. So I want the last one that's seen me that ends up happening there. So I'll go through every edge that remains. See if it's blocked. And I basically just find all the paths in the subtree and that information. Okay, so let's go back to solve tree and kind of see what's going on here. What I'm going to be doing is I just clear my path list, make sure it's empty, and I find all paths in the subtree. So starting from the start of the subtree, I just find all possible paths that end in this location. And now I'm not dealing with the subtrees, I'm dealing with lists, or a big list of paths. And I'm just going to take that big list of paths and I'm just going to update everything. So count number of paths ending at P. So I'll fill that in later. But basically, I want to count the number of paths that end in subtree I that start behind me in terms of my DFS. So if I go back here, I'm basically on this subtree I. So maybe I'll redraw this here. I'm going to have a data structure behind me that keeps track of all the paths behind me, and I want to count the number of ways I can end at subtree I. And then I'll have to run through it again. And what this will do is actually update all my paths. So I'll do that now. So T is true. This maybe isn't the greatest variable name ever, but this is basically when a path has a rest stop on it. So what I'll do is I'll just increment my variable here. And increment my variable here. Okay, so I have these tables. Every time I run this solve tree function, they're going to get, they need to be cleared, basically. So there are a couple ways I could do that. But the main thing I need to do is I need to not do like an array.fill here. I have to only do order component size of work. So if I make a mistake here, it could make my divide and conquer run outrageously slow. So I have to make sure that everything I'm doing is only on the order of the component size if I want my divide and conquer actually to work. So what I'll do real quick is I'll just go from offset. I have this value offset that's going to be my new 0. I already have offset. Oops. But offset is basically where 0 is. So I need to go from negative component size -1, because there are at most that many edges that I can go down and make things really negative. And then I need to go to offset size -1. So it's +1 here. And as long as my table is big enough, then I'm good. So I can just fill these. Okay, so let's explain what I'm doing here. So if you remember path, I'm pairing with paths before me. So I definitely, if a path is already satisfied, I could potentially pair it with another path that's already satisfied. That's fine. I can have multiple rest stops on a path. That's no problem. But I could have paths that are unsatisfied. They have paths that don't have a rest stop on them. And I only want to pair with those paths in one of two instances. Either I balance myself at the very top of the path, with the very top of the path, in which case I'm really a balanced path, even though I don't look like it. The other case is I'm already a balanced path myself, and that's when I want to pair with something that's not satisfied. And I also have to consider paths that end at the root. So that's what I'll do here is these are just paths ending at the root. Yep, going up to the top. Looks good. That looks good. Actually make some of this memory and see if it works. take away some of my Centroid code. All right, so I do need to still make my memory for, so offset is where 0 is. So I'm just going to make that n, because a path could go really negative or really positive. So my tables need to be size 2n. And so I'll just make them 2n plus 1. It gives me like 1 extra character of buffer in case I messed up my math. So I'll add an array deck there. And then have I seen this depth before? I'll add that here. Okay, that should do it. So what I'll do is I'll run it for my tree. I get number of paths is 1. So let's take a quick gander at this and make sure it comes out to 1. So I'll redraw my tree again and make sure my code is indeed working correctly on that case. So it's basically only pairing these two paths together. And that is not a balanced path in terms of, nope, that's wrong. What is my balanced path? I suppose it's this one, right? Yeah. So node 2 is the rest stop. It's basically found node 1 being paired here, pairing it back with this piece, and it appears to be going pretty well. Let's see, any other things? Well, one of the cool things about find tree or solve tree is if I want to test this, I could also test the case where the rest stop is right in the middle. You could see that being a bug. And this is why I test solve tree separately than the divide and conquer code. And that also comes out to 1. It works out fairly well. And so even if I root it at another place. So I could even root this somewhere like node 5, and it should still come out to 1. Actually, no, it shouldn't. Because node 5 is actually node 6. Okay, so here's why it shouldn't. Node 5 it's 0 index, so it's actually node 6. And you see it's not on the path here. So if I root it at node 6, then solve tree should not return anything. Same thing if I put in node 3, which is actually node 4. And that should come out the same. This should be a 7 over here. Okay. Well, it appears to be working. Let's see if I have any bugs. I'm going to send this one away and see if I can get it correct. That'd be impressive first try. If not, I've got quite a bit of debugging to do if I'm lucky this week. So I've solved this problem before, so yeah. Oh, oops. Well, that grading is in process. If you're doing USACO, you do not read from standard N. But I like to test from standard N because I like piping my files all over the place. So let's just check to make sure it's still working. Yeah. All right. see if I get this correct. And so you'll see on the problem, the bounds were up to 10 to the fifth. That's usually a good sign if you're doing divide and conquer on trees. So this algorithm is just n log n in runtime. And so we got it first try, no bugs this week. Excellent to have to deal with. So that's how you solve yin-yang paths. If you go to the Algorithms Live blog, I put up 2 extra problems that you could try. You could try this problem testers from CodeChef. It uses a data structure that you've already seen on Algorithms Live mixed with divide and conquer on trees. Very cool. It pairs very nicely with other things. It's all about solving that solve tree function. So if you get this, if you just take my divide and conquer boilerplate code, I guess you could say, or not boilerplate, but template or framework or whatever you want to call it, and you just modify that one little piece, you could solve testers by just solving the subproblems efficiently. Then there's this problem called race from IOI 2011. So this is a fairly popular technique. It shows up every now and again. And there are other classes of problems you can solve this way too. So that's it for Centroid decomposition. I'll take any questions if anyone wants, or if anyone has any questions to ask in the live chat. Let's see. And then next week, again, we're going to have Lewin back. He's going to explain yet another tree problem. And we're going to be discussing how this pattern of divide and conquer can be turned into a data structure. And one thing I hope that a lot of you will become aware of is anytime you have a pattern for divide and conquer, you can always turn it into a data structure. So if you see a divide and conquer pattern you really like, you can always make it handle queries by turning it into a data structure. And I hope we get to cover that next week. You could view the pattern of divide and conquer for merge sort as basically the segment tree pattern. You get segment trees if you turn it into a data structure. Centroid decomposition trees are just taking this pattern of recursion for centroid decomposition, divide and conquer on trees, and applying it to a data structure itself. So it should be really exciting to see. The problem we're going to cover next week, Lewin did centroid decomposition trees, and I found a way to solve it using just divide and conquer. So we'll talk a little bit about that next week. It should be a really good episode. So I hope to see you all then live next week.